Hi, I'm Andrew Duhovsky, and I'm talking to you about eye tracking measures of cognitive load at the EMICS workshop at Chi 21. Just some acknowledgements before I get going, before I forget. So some of this work has been done, supported by NSF, some donations from NVIDIA, and also with the help of SWPS in Warsaw and Tübingen in Tübingen. My frequent collaborators, Krzysz Krates, Iza Krates, Justyna Żurawska helped with some of the work done here, and Dr. Gerer in Tübingen, who helped set up some of the NBAC experiments. Okay, so cognitive load dates back to cognitive load theory, which I'll go over in a quick lit review. And then I'm going to try to give you an overview of some computational approaches, some pitfalls, and how to do some of the things, including microsaccades, which I'll finish up at the end. I have a bunch of results I'd like to talk to you about, but I don't think I'll have time. So I might try to answer those in the Q&A session. All right, so why bother with cognitive load? Well, there are actually quite many applications on where cognitive load measurement could be useful. A lot of papers at Chi show up on this, from automotive learning domains, automotive, flight safety, of course, surgical training, just general human-machine interaction, geoinformation systems, and of course, driving, if we could detect the eye and pupil, or maybe microsaccades. But anyway, if we can get cognitive load in any of these applications, it could be useful in tailoring the system to alleviate cognitive load as experienced by the user. So cognitive load theory dates back to Sweller and possibly beyond even, but this is the one where I guess people most rely on in terms of what cognitive load is and how does it show up, how does it manifest itself. And so Sweller proposed a production rule computational model which really involved memory and essentially or other brain resources, saying that if you're taxing your brain under heavy or task difficulties, then eventually you're going to run out of resources. And that's the gist of it. And what resource? Well, memory is an example. All right, so Sweller 94 also identified intrinsic, extraneous, and germane, and there's some debate as to which load are we actually measuring with an eye tracker. And so that I will defer to the psychologists. But a lot of times while eye tracking, people will refer to the Hess-Poltz study of 1964, which showed that pupil dilation responds to task difficulty. But it should be mentioned here that a lot of this work is based on the use of pupillometers, which are slightly different devices than eye trackers. And you'll see here that they run at they used to run at 2 frames per second. This was back in the 60s, right? And I believe they were devices that you kind of hold up to the eye and you can get a very nice crisp view of the pupil diameter. And so Hess-Poltz's infamous study, as I call it, gave subjects, all 5 of them, multiplication tasks. And so the harder they were, that was the indication of cognitive load. All right. Kahneman Beatty is also popularly cited, showing that pupil diameter, again, responds to cognitive load. And they termed this as the task-evoked pupillary response. And here they used a television pupillometer. So now it's slightly faster in 79 at 20 hertz, but still not as good as eye trackers are today. And of course, in the 80s, it came up that, well, are we measuring the light response of the pupil as it dilates in low light and as it constricts in high ambient light? Or are we measuring the psychosensory reflex? And that's the one that we want. And so up to this point, really no mention of eye trackers as of yet. But again, pretty good review of pupillometry, and I would suggest that you read these to find out why is it that pupillometry or the pupil reflex, psychosensory reflex, how does it relate to brain function? Pacikovic is also a very good reference, 2016, that really did a nice link of the LCNE system and said that, well, baseline pupil diameter is related to tonic response of the LCNE system. And then what we're really after is the phasic response, the transient response. So it's like the response to task versus baseline. And you'll see that indeed for pupillometric measurements, we do want to compare the difference in pupil diameter to baseline. Okay, so going back to 95, that was one of the first eye tracking uses by Hiona, and he used this inter-trial measurement relating the measurement of pupil diameter to baseline. Klingner was one of the first eye tracking papers that I was aware of in 2008 at ETRA, where they showed a really nice use of an eye tracker to show intra-trial, so within the same trial, response to cognitive load, but also highlighted the 2-second delay, and something that one must be aware of, that the response might be kind of slow. Flipping back to Pacikovic again, in terms of pupil diameter, they also looked at the low frequency to high frequency ratio that'll come into play later for the LIPA analysis. And one reason they did this was because they wanted to tease out the response to light. And so here they used different screen backgrounds, gray versus white as an example, to try to get the phasic response. So here the graph shows the expected response versus baseline, or the control as they call it, right? And so here we do expect some kind of response. And so they used the rather difficult Toulouse N-back task, which is like the N-back, where you have to remember 1 or 2 steps back. That's the N. But what is it that you're presenting? Well, normally you present a letter, A, B, C, D. And then if I say B, then that would be like a 3 back. But here they did, they combined, I guess, kind of the old arithmetic task in here. So you had to remember the computation, which I think was quite difficult. But anyhow, they got pretty good results. And again, to highlight, the ratio would be lower with the greater cognitive load. So as you can see, the dashed line here is indeed lower than the 1-back task, which is the solid line. All right, so 2 key problems with pupil diameter, of course, luminance. And so Pacikovic addressed this by looking at different screen backgrounds, gray versus white. But a lot of people don't bother even measuring, taking a light meter to the screen and telling us what the luminance is. And so I think they ought to. Meanwhile, if you look at what eye trackers do, they will measure, of course, pupil or gaze location, but they do this by finding a pupil center. And as the eye looks away, you get pupil diameter distortion. And so it's not a huge deal because you can apply Hazen-Petrov's correction to this. But again, one needs to be aware of this, especially at large visual angles. And so here, I've read papers where they talk about 10%, 0.1 difference in pupil diameter using an eye tracker and saying that, wow, that's huge effect. But 10%, well, that could mean the off-axis pupil diameter ratio that you're measuring instead, right? So you have to be careful. All right, and insofar that that goes, Eilink even said that, well, if you're going to measure pupil size, you should ask your participants not to move their eyes, which kind of defeats the purpose of an eye tracker. Anyhow, Stark, going back to Lawrence Stark back in the 50s, he was a pioneer of eye tracking research. He had a nice paper on pupil unrest, which is the oscillation that the pupil does, the pupil diameter does, this kind of thing, akin to what a rodent does with their nose when they sniff the air. And so that is, the ICA's computation is more or less based on that. So Marshall's index of cognitive activity, the ICA, measures this amount of oscillation. And you can see on the right there that in the math, there is expected larger and more frequent is the key, oscillations than with respect to doing nothing. And so they did compare light versus non-task in their experiments. And so they are looking essentially at the number of edges that you see of the pupil oscillation, which is great, but they referred to an unpublished manuscript, which I've never been able to find. So the only way I could find how to implement our version of their ICA is based on her patent. And then they talk about various ways of things that they use, Dupashi's 8 wavelets, you know, some of the things that they talk about. And so it's a good read, but not as much detail as one might expect. So possible computational approaches to sum up intra-trial, within-trial differences with respect to baseline, inter-trial again with respect to baseline. So those are both baseline related measurements. The IPA is our version of the ICA from CHI 2018, which worked okay in a fixed gazed task, but didn't work very well when we let the eyes move freely. And so the LHIP, or LIPA as we referred to it in CHI 2020, was responded better. And then of course there are microsaccades. So I will refer you to the CHI 2018-2020 papers for the computation of the IPA and LIPA. Here's a quick, very quick, I got 4 minutes left. So it's basically a wavelet analysis of the pupil diameter signal. And so the wavelet looks like this, the wavelet signal, but it is based on really the scaling function, which I'll tell you in about a minute here. And from both of those, you get the wavelet transform of the pupil diameter. But it boils down to just using wavelet filters, which are nothing more complicated than finite impulse response filters, like the HAR over on the right, or the Dupashi's 4. Dupashi's 8 is, they're just longer. We use Simlet 16, for example. But still, you've got the wavelet analysis, and you have the scaling function here. So you get two versions. So here, the scaling function is the fuzzed out version of the image, and the wavelet coefficients are the edge images. And if you do it at another level, you essentially get different frequency octaves. In 1D, similar idea, you can get a smooth version of the signal that's been popularized in computer graphics. So for us, for the IPA, to find these edges, the spikes in the signal, we also added in modulus maxima detection, which just means that the edge needs to be greater than or equal to both of its neighbors, and strictly greater than at least one of them. And then if you do that, then you can threshold on top of that, and then count the number of spikes. Here's the algorithm. It's not very long. And here's what it looks like. So on the left is the easy trial wavelet approximation. That's the scaled version of the signal. You can see that it doesn't seem to change very much at 3 levels. You need, to go, depending on the length and the signal, you can go really farther down. On the right, difficult trial approximation also doesn't seem to show you much difference. But if we do the coefficients, the actual spikes and then threshold on those, you can see that in the difficult trial, we do indeed get more spikes, as Marshall suggested we would. The LHIPA is a little bit more complicated, where we take the ratio of the low to high signal as per Pesacovich, but not too much more difficult. You essentially use this ratio and compute in a similar way. So those are the IPA, LIPA, and then an inter and intra trial based on related measures of cognitive load. But there's also microsaccades, and this is Siegenthaler had a nice paper on this. So given the more difficult task, microsaccade magnitude would go up, microsaccade rate would go down. So the rationale behind this is that if you're fixating something, trying to fixate something, and you're really thinking hard, then you take away resources from the fixation. And so you're going to decrease the number of microsaccades that you can issue. So they slow down, but you get bigger ones, which tries to correct fixation location. So I'm going to skip this slide, but this is what they basically found, and it's to do with superior colliculus activity. And again, it's the best thing is to show what are the microsaccades. So here is the Pritchard 1961 paper, really good on showing you the mosaic of the retinal receptors. And so you get tremor drift and microsaccades are the small saccades that move your gaze back to where you want them to be. What it looks like is kind of like this. You can find them, but you need a high sampling rate. Here's the algorithm. It's not ours. It's been around for a while. You need a high sampling rate to get the microsaccades, and then you want to plot out the microsaccade main sequence to make sure that you're actually getting them. So this is the telltale. Okay, so I'm out of time, 20 seconds left. So these are the approaches that I have, I know about, and some pitfalls and some what works, what doesn't, and I'd be happy to answer questions. I've got a bunch of experiments that I could talk to, but I just don't have time, so I'll save for the Q&A. Thank you very much.